Alright guys, welcome back. Today we're going to continue talking about surface area of SUCS. Just recall again, SUCS equals to solids of uniform cross-section. The general formula for surface area of SUCS, we talked about that yesterday during the life lesson, it was 2b plus hp. In this case, the b represents the base area, and h represents the solid height, okay, the height of the solid, and p represents the perimeter of the base. So it really depends on what shape we're talking about and how it's oriented. The base, h, and the perimeter can be in different locations. For example, in the first case, right, if you're standing upright, right, by actually stacking from the bottom to the top, then this, okay, where you actually normally think the base is actually where the base is. Right? So this is the base area, right? So this is where your B is. You basically just need to find out the area of that. And then our P is basically the perimeter of the B in this case. Okay, so that's just a perimeter. You basically just add all the four sides. And then your H is basically just the height of the building. But on the other hand, sometimes our SUCS can be oriented in a different way. For example, in this case, right? In this case, we're actually stacking from the front all the way to the back with the same area of trapeziums in this case, right? So in this case, this is where your base is actually, right? You probably think your base is this one over here, but if you have your base here, then when you stack downwards, you realize that the areas are all different, right? You're gonna have a smaller rectangle, and on the bottom, you're gonna have a really big rectangle, right? So that's how you can get a trapezium at the end, right? But that's not what we want, because we want uniform cross-section, right? We want all the way the same from the beginning to the top. So that's why we need to choose the trapezium in this case. So this is our base area actually. That means your P will be basically the perimeter of this trapezium, right, which is also not hard to find. And then when it comes to height, in this case, we're actually talking about the depth, right? So this is actually the height, right? If you imagine that you stand the whole thing upright, then that will become the height. So that's basically all about this formula. Today we're gonna talk about surface area for cylinders. Right? This is actually another SUCS shape, right? Because in this case, what I'm having a circle on the bottom, and I keep going circle for every single level. And then at the top, at the end, I still have a circle. So that's why we call it SUCS as well. So now we're going to find out the surface area for this. Actually, our general formula for SUCS also works here. So we can actually copy the whole thing down over here. Except in this case, our B, P, and H are actually meaning specific things in this case. Okay, so let's go ahead and find out what our B, what our H, what our P in this case. Right, so our B is basically either the bottom one or the top one. I'm going to choose the top one. Right, so this is basically my B over here. So it's a circle. Right, this is basically an area of the circle. So you can take a little note over here. Tell yourself that this is actually the circle area, isn't it? So your base area is basically just a circle area. So what is my circle area, right? How do you find the circle area? Pi r square. And then you have two of these. So that's why we have 2 pi r square in this case. And then we need to plus the HP. Okay? In this case, what is my H? Well, my H is nothing really special. It's basically just my H. In this case, it's capitalized, but we will just write the lowercase h over here. All right, so nothing different in this case. But what is our P in this case? Our P is basically the perimeter of the circle. We actually have a very special name for the perimeter of circle. We call that the circumference. So in this case, the B actually means the circle area. The P actually means the circumference. So what is the formula for circumference? You are exactly correct. This is 2 pi r. Right? So my circumference is 2 pi r. The circle area is pi r square. Okay? So after rearranging, you will realize that your surface area for a cylinder is very special on its own. Okay, it's 2 times pi r square plus we have 2 pi r h. Okay, whichever you like. Right? If you like this one, you can go with this one. If you like the other one, you can go with the other one. It doesn't really matter. So now let's just look at a few examples. The first one over here, we want to find the surface area for this cylinder. So let's use our formula. SA equals to 2 pi r squared plus we have the 2 pi r, which represents the circumference, and then multiplied by the h. Right? This whole thing over here will take care of your lateral area. Alright, so we plug things in. In this case, my r is equal to 6. So we got 2 pi 6 squared plus 2 pi 6 h in this case. The h is the thickness in this case, right? So what we do is we do the p and times the h, and that will give you the whole lateral area. Okay, so that's equal to 15 in this case. So you punch everything to the calculator. The answer is 792 centimeters square. Okay, now the next thing that we want to talk about is something that we probably need to be a little bit careful, because a lot of times in our real life objects, they are in cylinder, but they are cylinder in a different way. Right? For example, in this case, you could actually be a cylinder with no cap and no bottom. Right? For example, if you're a tube, right? If you're just basically a hollow tube or a hollow hose, then you are expecting your tube to be open-ended on both sides, right? So that the water or the airs can go in. So in that case, if we are talking about the surface area of this object, we are actually only talking about the lateral area. So if you open up this cylinder, you will realize that we don't actually have the cap, right? We don't actually have the base over here. What we have is only the lateral part. So in this case, my surface area, it used to be 2 pi r square, right? Because it represents, the 2 pi r square represents the cap and the base. But in this case, I don't have neither of them. So what I only have left is the lateral area. And then the lateral area is just the 2 pi r times the h. Okay, so that's it for my surface area. Now similarly, we have two other cases. The next one is you have an open can, for example. Okay, a can bottle that is being opened. In that case, you actually don't have the cap, but then you have a base, right? You need to have that in order to contain something, so you need to have a base. So the base will be existing in this case. So that means this part we will need to consider. We don't have the top, so we don't need to count it in. And then we always have the lateral area in this case, right? Of course, because that's a whole body. Right, so in this case, what I have, instead of 2 pi r squared, I only have one of the pi r squares. So in this case, I'm only going to have 1 pi r squared. Okay, of course, you can omit that 1. Plus the 2 pi r times h. So I guess we can start seeing the pattern over here. The last one is basically the one that we talked about before, right? That's basically saying that if you completely seal the whole can, right, then in this case, you will have the cap, you will have the base, and of course, you will also have the lateral area. So in that case, you do actually really need to count everything in. Now, so first of all, you will have 2 of the pi r squares, and then you will plus the lateral area. The lateral area is basically just the circumference times the height, as usual. Okay, so these are 3 different cases. One is you actually have 0 pi r square, which is this case over here. The other one is you have 1 of the pi r squared. The last one is you have 2 of the pi r squares. Okay, so these are the 3 different cases that you might see in questions. So in this case, we have Jane trying to paint a cylindrical tin cans, okay, which has height 12 and diameter 8. Okay, she is painting top, bottom, and sides. So in this case, we can know that and we're having all 3 parts that we need to consider. Okay, so we have a cap, we have a bottom, and then we also have everything. We have everything, so we need to take everything into account. So if we draw a little picture, that's basically what we want. We want a cylindrical shape in this case. We want to consider the base, the top base, and also the bottom base. Okay, and then we also need to consider the circumference, and then we need to multiply by the height. Okay, so that's what we want. So let's use our formula. In this case, we actually do have 2 pi r squared, right? So 2 of the base areas, and we plus the 2 pi r, which represents the circumference, and then multiply by h. Okay, so we'll plug everything in, but be careful that they're giving you the diameter instead of radius, so we convert that to radius. Our radius is 4. Okay, so we got 2 pi 4 squared plus 2 pi 4 times 12. Okay, punch everything in. The answer is 402.12, approximately, centimeters squared. But that's not it for the question, because it's saying that Jane has enough paint to actually cover an area of 5 meter squares. So we're asking how many cans can she paint if she's not tired at all. So what we want is, first of all, we want to convert, okay, because all these units are in centimeters, but we're having this meters. So what we're having is basically 5 meters square to be converted to centimeters. Okay, so let's convert that. So 5 meters square, we want to convert from meter to centimeters. Remember that 1 meter square is equal to 100, but double amount of the zeros. So that's how we can cancel the meter squares, and we're left with cm squares. So you multiply by 10,000, you actually get 50,000 centimeter squared. Okay, so she can actually paint that much cans, but each one of the can only takes up that much. So that means you can actually paint a lot, but how much? Right, 50,000 centimeters squared divided by 402.12 for each one. Right, that will give you approximately 124.34. Right, so that's a lot of cans. But of course, you cannot paint 0.34 cans. Right, how many complete cans can you paint? Our final answer should be 124 cans. Okay, you cannot paint 125 because you don't have enough to paint that one more. Right, so that'll be the answer for this question. Okay, the last question of the day. Let's look at a pot. Right, this is a saucepan. And just the fact that it's a saucepan, and we're also excluding the handle, we can quickly realize that we don't actually have a cap on that. Right, so we're basically just looking at this shape by itself. Right, so that means we have a bottom, we don't have a top, and then we have a lateral area. So in that case, my surface area should be just 1 of the pi r squares, right, which represents the one on the bottom over here. So we're only taking care of that one over here. There's nothing on the top. And then we'll plus the circumference times the height. Okay, so that's our plan. Right, so we got 1 of them, 1 of the pi r square already. And then we need to plus the 2 pi r, which represents the circumference. And then we multiply by the height. And then we plug everything in. Right, so in this case, by the way, here they're telling you the diameter again, so we need to convert that. In this case, our r is basically equal to 25 over 2 equals to 12.5. Okay, so pi times 12.5 squared plus 2 pi 12.5. H is 11. Right, just this guy over here. So you punch everything in, you will get 1355 centimeters squared. And that's it for this question. So that's it for today. I'll see you guys tomorrow during live lesson. Peace.